Hello students, welcome back. We just completed section 1. Now let's go to section 2, integral domains. And integral domains are important, but this section is going to be short because we covered most of it already. Here's a definition, or more precisely, a reminder. An integral domain is a commutative ring with unity with no zero divisor. Here's some examples. Z is an integral domain. Okay, all right. Commutative ring with unity with no zero divisor, but not MZ for m greater than or equal to 2. They're all commutative rings with no zero divisor, but in general, they don't have unity. When m equals to 1, yeah, okay, 1 is the unity, but for 2 or higher, then no unity. Now, the polynomial ring Rx is an integral domain. What is this? It's a ring of all polynomials of real coefficient, and it's an integral domain. And so is Qx or Cx or Zx. As a matter of fact, we can prove this. If D is an integral domain, then the polynomial ring given by the coefficient from D is an integral domain too. So D is an integral domain, then we can prove that dx is an integral domain too. I think we're going to do that a little bit later. It's not too bad, so I'm not going to push this over to abstract algebra 2. But as for this one, for unique factorization domain, yeah, this one I'm going to push over to abstract algebra 2. How about this one? The ring of square matrices of size m with integer entries. This is not an integral domain, and the reason is it has some zero divisors. And here's some examples, like this, or that. Oh, by the way, not only do they have the zero divisors, the multiplication is not commutative either. So okay, all right. In this case, the general linear group, in this case, the determinant is non-zero, so they're all invertible. So there's no zero divisor here. But this is not an integral domain either, because the multiplication is not commutative. This one is actually a skew field. Oh, excuse me, we have Z there, so sorry about that. If this is R, then okay, all right, skew field. But for Z, then no, it's not that either. Okay, in that case, we have multiplicative inverses too, so it's a division ring, but not a field, because it's not commutative. Multiplication is not commutative. Zm is an integral domain if and only if m is prime. We saw this before. Zm is a field if and only if m is prime. We set it up and proved it in lesson 11, I think, and that was rather significant. And every field is an integral domain. Yeah, I mean, we proved it over here. Every unit is not a zero divisor. So if you have a field, then all non-zero elements are units. So none of them is zero divisor. So yes, there's no zero divisor. Speaking of field versus integral domain, Here it is. Every field is an integral domain. Yes. So a times b is equal to 0 when a is non-zero, and we have to prove b is equal to 0. Then b is, let's rewrite like this. B is 1 times b, and 1 is 1 over a times a. But then again, if you use the associativity, a times b is 0, so 1 over a times 0, so that's 0, so b is 0. So there cannot be any zero divisor. Here's a summary, by the way. Integral domain is here. Field is smaller category here. It's a subcategory. Now, here's an interesting statement. Every finite integral domain is a field. Let's go back to the Venn diagram. Field inside, integral domain is a little bit broader, but everything outside here, all those are infinite integral domains. Finite integral domains fall inside because they're all fields. And then let's go back to 1.5 and 1.6. A unit can never be a zero divisor, and equivalently, a zero divisor is never a unit here, so we prove that. And the converse does not hold in general. Not a zero divisor, then not a unit? Not necessarily. Not a zero divisor, but still it doesn't have to be a unit. So there are plenty of examples. But for Zm, the converse is true. Not a zero divisor, then yes, it's a unit. Because zero divisor means, A and M are not relatively prime. Unit means A and M are relatively prime. So not a zero divisor, then not relatively prime. So it's relatively prime, you see. So not a zero divisor versus a unit means actually the same thing for Zm, and we proved it hard way. But here's a little bit more clever way for a little bit more general situation. Every finite integral domain is a field. Not just Zm, but every finite integral domain. So this is a lot stronger. Amazingly, this proof is going to be a lot easier than what we did in 1.5 and 1.6. 1.6, I mean. Let's try to prove it. Choose any non-zero element A from the given finite integral domain D. And then we must prove that the multiplicative inverse of A exists. Okay? We have to prove that D is a field, so any non-zero element is a unit. So how do you prove that? We devise an ingenious map like this. A certain map, f, from D to D, defined like this. F of x is A times x. And let's see, you don't really have to worry about the algebraic structure. Does it preserve addition, multiplication? Nothing like that. The proof is going to be set theoretic. What we're going to do is to prove that this map is a one-to-one map. How do you prove that? Well, one-to-one map, what do you mean by that? If we select two different elements from the domain, then we get two different elements in the range. So if we take counterpositive, if the function values are the same, then they must have originated from the same domain. In other words, we want to prove this. That'll complete the proof of f being injection. Make sense? Same function value, then they both must have originated from same original. How do you prove that? We use the cancellation rule. F of x is equal to f of a means ax is equal to ay, and then we use the cancellation rule, and yes, you can do that because there is no zero divisor. Remember, a is non-zero, so we can use the cancellation rule. So this map is 1 to 1. Okay, all right. What we have is a 1-to-1 map from D back to D, which is a finite set. So this is not only 1-to-1, but it is onto as well. Does it make sense? If it is infinite, it doesn't have to be. You can devise a map from, say, entire R into itself, not onto. But for finite set, no, not really, because you see, this is a 1-to-1 map, and D has, say, 5,000 elements. Then the map will send over the 5,000 different elements. And the range or the image will cover entire D. Same number of elements, because D is finite. You see, that's critical. D being finite is a critical observation. So, this is a bijection. So, it covers everything, and in particular, f of some b is 1. What do you mean by that? F of b is 1, so a times b is 1. So b is 1 over a, the multiplicative inverse that we were looking for. This completes the proof. Every non-zero element is a unit. Every non-zero element has a multiplicative inverse. It's not a constructive proof. There exists a certain b because of D being finite set. So the conclusion, every finite integral domain is a field. So for example, Zm being an integral domain and Zm being a field, they actually mean the same thing. And not just for Zm, but every finite integral domain is a field. So that proof, as a matter of fact, greatly simplified what we did in 1.6. This one, 1-to-1 and onto, this one, the necessary and sufficient, and this one, necessary and sufficient, we have to prove 4 of these. And as a matter of fact, neither one was easy. None of one was easy, actually. But if you go over to this, every integral domain is a field, then everything here becomes a trivial observation. It's amazing. Okay, that completes section 2. We're going to discuss section 3 and 4 in separate videos.